So let's start this week's lectures by solving the quiz from the previous week. Okay, I think we did not have time to solve it in detail, so let's start with that. Right. So what was the question? Let me remind you. The question was that I have a small ball of mass m moving with velocity v, as shown in the figure. Particle hits the rod at its end point, making a 45-degree angle with the rod. If the particle sticks to the rod after the collision, find the angular velocity of rod-particle system after the collision. Now, what's our guiding principle in solving this problem? Is energy conserved during the collision? No, it's not. The two objects sticks to each other. Is momentum conserved in this collision? No, it's not conserved because there is a nail that's fixing the rod to the table, right? That's going to give some forces. But angular momentum is going to be conserved. Let me try to draw this figure a little bit bigger. So this particle is moving on a line with velocity v, which has mass m, and the angle between the rod and the trajectory of the particle is 45 degrees. So what's the initial angular momentum of the system? That's what we have to find. Now, is there any angular momentum coming from the rotation of the rod? No, it's just stationary. So all the angular momentum must come from this small mass, point mass, moving. So it must be r cross p. Obviously, here, let's remember what r vector is. R vector was the vector from the pivot point to the particle. So r cross p is going to be, well, p is like this. First, let's check the direction. R cross p coming out of the board. So it's a counterclockwise angular momentum. And that's pretty much what we expect. I know from daily experience that if this mass is going to hit my rod, it's going to start turning counterclockwise. So let's try to find the direction. Find the magnitude of this. Now, in general, r cross p is not going to be easy to, at least I don't know the angle theta here so well, right? However, what do I need? I need the following. I need r magnitude, p magnitude times sine theta. Now, if I actually look at the distance of closest approach, what's this length from the pivot point to the point of closest approach? There's a right triangle here. It's going to be r magnitude sine theta, exactly what I actually need. So if I write this as r magnitude sine theta times p magnitude, that's going to be okay. And what's r sine theta? The length from the other side of the triangle, the length over here is L over 2. This is pi over 4. So r sine theta is what? So there's another right triangle here, right? Another right triangle here. So apparently from geometry, r magnitude sine theta always remains L over 2 times sine pi over 4, which is going to be square root of 1 over square root of 2. So it's going to be L square root of 2 over 4. Does everyone follow the logic here? So I know that theta is changing as this particle moves on the line. I know r vector is changing, but apparently r sine theta is not changing because I can relate it to this other triangle. Okay? And again, angular momentum is momentum times the distance of closest approach to the pivot point. Good. So now I can write this here. P magnitude is mv. R sine theta is L square root of 2 over 4. So this is my initial angular momentum. Now we need to find the final angular momentum. In the final case, I have this rod. I have this particle sticking to the end. And they both rotate with omega. What will be my final angular momentum? My final angular momentum will be I rod times omega plus, what will be the velocity here? The velocity of the small mass m. The distance from pivot point is L over 2. So velocity will be omega times L over 2. So angular momentum is what? M omega L over 2 is the momentum of small m. Its distance, r cross p, right? R is here, r cross p. It's a right triangle. So m omega L over 2 squared is going to be my angular momentum. In other words, you could just as well say, hey, I can think of the total system, the combined system of the small mass plus the rod, that would have an moment of inertia of I rod plus ml square over 4 times omega. So if I equate these two, initial angular momentum is equal to final angular momentum. We found the first one to be mvl square root of 2 over 4. That's going to be, and I need I rod around the center of mass. I remember it to be m L square over 12. M L square over 12. That's going to be m L square over 12 plus small m L square over 4 times omega. I was asked to find omega, so I will have m square root of 2 divided by capital M over 3 plus m v divided by L. Right? Good. So in every question, we need to determine which of our quantities is actually conserved. What three quantities do we have? Energy, momentum, and angular momentum. Let's solve one more example, again in a very similar setting. Okay. Again, on a frictionless table, I have a rod, uniform rod, fixed from one end. Uniform rod fixed from end point. So the length, the mass of this is m, the length is L. I have a small mass m coming in with velocity v at exactly L over 3. Okay? small mass m makes an elastic collision with the rod. Find the angular velocity of the rod and the velocity of m after the collision. So, does everyone understand the question? It's pretty much the same setting. I have on a table, I have a rod and a small particle. The small particle will come, hit the rod. But now we're told that this is an elastic collision. All right. So after the collision, what do I expect? My expectation is that this rod will start rotating with some angular frequency omega to the left, and the small mass m goes back with some velocity v prime. Okay? So I am asked to find what's that frequency, what's that angular velocity, and what's that velocity after the collision. So what are my guiding principles here? What are the conserved quantities? First of all, because I have only one pivot point, there will be no net torque on the system, right? Which means angular momentum is conserved, right? But angular momentum conservation can give me only one equation. How many unknowns do I have? I have omega and v prime. So I have two unknowns here. I need one more principle, and it's staring me at the face because the question explicitly says this is an elastic collision. Elastic collision means energy is conserved, right? Now, what is my initial? Yes, question.
I'm talking about when we say elastic collision, I'm talking about angular momentum or
Neither. Elastic means energy is conserved. Okay. In this problem, it turns out angular momentum is conserved, energy is conserved, but linear momentum is not conserved. Why not? Because there is a nail which is actually fixing my rod to the table. Okay. But elastic tells us something about the details of the force during the collision. Okay. The force between these objects is so that no energy is converted from mechanical energy to heat. So maybe this is a very elastic ball or that's a very elastic rod. So when they collide, they collide elastically. That's what it says. Question?
do we take the frame of reference with respect to the pivot?
Louder, please.
Do we take the frame of reference with respect to the pivot?
That's the best scenario. I mean, that's the best thing we can do if there's a pivot. If there's a fixed pivot, you should always try to work in the frame where that pivot is actually not moving. Okay? But that's an important question. We'll come back to that during the next lecture. Okay. Now, angular momentum is conserved, energy is conserved. So let's start with the initial case. What's my angular momentum in the initial case? The rod is not rotating. I only have angular momentum coming from the mass. Now, I will not calculate R cross P again. You could if you want. But I remember that this is going to be m times v, momentum of my particle, times its point of closest approach, which is L over 3. If you do not believe me, which is okay, if I actually calculated R cross P, I need the angle theta here. R times sine theta will again be L over 3. That's why I can so comfortably write L over 3 times mv. That's my initial angular momentum. And which direction is this angular momentum, clockwise or counterclockwise? It is counterclockwise, right? Or if I wanted to show it as a vector, it's coming out of the screen. Good. How about initial energy? This is on a table. I don't have any potential energy. What's the kinetic energy of the rod initially? 0. It's not rotating. How about the particle? 1/2 mv square. Excellent. How about the final situation? Let's come back to the final situation. What is my final angular momentum? Now, I have I rod times omega. And which direction is that angular momentum? Clockwise or counterclockwise? It's rotating counterclockwise. That's good. How about the angular momentum of the small particle reflecting back? It's again reflecting back from L over 3. So it must be mv prime L over 3. But is the angular momentum of the small particle clockwise or counterclockwise? Now it's clockwise. It's a rotation. If you want, let's do R cross P here, just to get some. This is R. This is P. If I do R cross P, it's into the system, which actually tells me it's a clockwise angular momentum. So I rod times omega was counterclockwise. mv prime L over 3 is clockwise, which means I should put a minus sign between them. How about the energy, final energy? Well, I have 1/2 m v prime squared. That's the kinetic energy of my point mass. How about the kinetic energy of the rotation of the rod? What do I need? 1/2 I rod times omega square. Let's also remember what's I rod. It's not from the center of mass, it's from the edge. And I remember that it was m L square over 3. All right? Good. So what do I need to do? I need to actually just conserve angular momentum, which is going to be L initial is equal to L final. L initial was mv L over 3. And L final is, let me write it nicely, m L square over 3 times omega plus, not plus, minus m v prime L over 3, right? So apparently v prime, 1 power of L also cancels. V prime is what? V prime is m L omega divided by small m minus v. Right? Now I need to conserve energy. Energy initial is equal to energy final. 1/2 m v square is 1/2 m v prime square plus 1/2 m l square over 3 omega square. Are you following me? I'm a little bit concerned. How many of you are able to follow what I'm doing on the board? That's good. Okay, maybe I shouldn't be concerned so much. So now let's cancel these 1/2s, and I can actually put v prime into the expression for v prime here. So I have m v square equals m small m over large M over small m L omega minus v squared plus m L squared over 3 omega squared. Let's do that. So I have v square equals m square over small m square L square omega square. Sorry? Oh, okay. So I canceled from the first two terms and added it to the third term. Okay, maybe let's just leave it like that. Okay. Let me do it slowly. I have m v square equals m times capital M square over small m square L square omega square minus 2 capital M small m L omega v plus v square plus m L square over 3 omega square. Now, here's the nice thing. M v square is m. I'm just writing it in reverse order. M v square minus 2 m L omega v plus m square over small m L square omega square plus 1/3 m L square omega square, right? The first two terms cancelled, so this is 0 is equal to minus 2 m L omega v plus m L square omega square 1/3 plus capital M over small m. Right. Now this equation has two solutions. Let's write them. I have omega zero m L. So here I have L omega 1/3 m over small m minus 2v. So this ml is basically not important. So I have two solutions. Omega is either 0 or omega is 2v divided by 1/3 m over small m times L. Which solution should I take? Second one. Why? What's the first solution? It's the initial state. Excellent. So this is the initial state. So we have found omega as this nice. Let me write it a little bit differently, right? 6 over m plus 3m. V over L. I was also asked to find V prime. V prime was m L over m, capital M divided by small m, L omega, right? Minus V. Minus V, which I'll write as 6 m divided by, no, minus V, just V. Excellent. So now I can actually put this in. I'll have 6 m divided by 3 V minus V, or 6m 3 capital M plus m minus 1 times V. I can even write this in a better way. It's 3m minus m, 3m plus m times. Not m, 3m. There was a question. Wasn't there? No? Yes? Louder. Capital M divided by small m, how did they disappear? So let me do it slowly here, that term. M over small m L, and for omega I write 6 small m divided by m plus 3m V over L, right? Small m's cancel, L's cancel, and that's what I get. Okay. More calculations you do, the faster you'll get in doing algebra. Okay. Same thing with calculus. The more you integrate, the faster you will get. Okay. Now here's the interesting thing. Let's check. So let's put those results in. Omega is 6m divided by small m plus 3m. V over L, and V prime is 3m minus small m plus m. Did I reach my goal? Yes, everything is expressed in terms of given quantities. How about units? What should be the unit of omega? Omega should be 1 over second. So in front I have kilogram divided by kilogram. V is meter per second. L is meter. So that's 1 over second. It checks. How about V prime? That should be meters per second. This is kilogram divided by kilogram times meter per second. So units also check. But here is something interesting. First of all, what would you expect this omega to be if the small mass was very, very light? If I had a steel bar and I'm sending just an atom to it, right? There would almost be no rotation. So in that limit, I would expect omega to go to 0, and it does. But here is another interesting limit. What happens if capital M goes to infinity? When capital M goes to infinity, that's almost an immovable bar, right? So whatever mass I throw to it, I expect it to bounce back. It's like hitting a wall. I expect it to bounce back with exactly the same velocity it actually came in. So in that limit, I would expect v prime to be exactly v, and that also checks. Okay? Doesn't it? It does, right? Limit m goes to infinity of the expression for v prime is v. But here is something more interesting. I did not specify anything about the ratio of the masses in this problem, small mass and capital mass. So my problem, my answer tells me that v prime is 0 if m is equal to 3m. So that's actually kind of interesting. If I send a particle with 3 times the mass of the rod exactly to L over 3, after the collision, the following happens, apparently. My particle just sits there, and now the rod is rotating. Now, and what's more interesting is that if I actually send this 3m a little bit below that L over 3, okay, then it will actually start going forward. If I actually send, no, it will start going back. If I send it above L over 3, it will keep going forward, right? So sometimes people who hit things with rods, I mean, like cricket players or baseball players, they say they hit the ball at the sweet spot. So they believe that there is a sweet spot on their bat which sends the ball flying with the best velocity. So in this problem, there is again a sweet spot like this. If I actually hit this rod exactly at the correct point, all the initial energy of the ball, if you want, is transferred to the rod. So you can imagine a reverse process. I could actually transfer all the energy of my rod to the ball. Okay? So this is called, so these sorts of problems are called sweet spots. Okay. Now, let me solve one more example, and then I'll actually I want to discuss something in more detail. Two masses both, or let's like this, two identical masses are tied to a pivot point as shown. So I have two masses m and m. They are rotating with omega on a frictionless table. So let's say the length of these, I'm going to use something different. I will call this small l. Find the tension in both strings. If the first string breaks, find the center of mass velocity and omega of the masses. So they are initially rotating with omega. The first part of the question is very easy. Let me right away solve it on the figure. So both of them are tied with strings to the to a nail on this frictionless table. They are rotating. So can you tell me what are the velocities of these objects? Which one has higher velocity? The outward one has higher velocity. V1 will be omega L. V2 would be 2L omega. I'm thinking that the width of the mass is actually very, very small. Okay, I don't care about that. Now, what are the accelerations of these objects if they are doing uniform circular motion? This is going to be V1 square over L, and this is going to be the acceleration. A2 will be V2 square over 2L. So if I draw free body diagrams here, there is T1 and T2. So the small mass, the first mass, is pulled left by T1, pulled right by T2, and it has an acceleration A1, which is apparently omega squared times L. How about the second mass? The only force on the second mass is T2. Its acceleration is to the right, which is apparently just omega squared times 2L, right? So Newton's equation for the second mass is m times omega squared times 2L is T2. For the first mass, m omega squared L is T1 minus T2. I was asked to find T2. Apparently T2 is 2m omega squared L. And for T1 here I can solve it as m omega squared L plus T2. So T1 is 3 m omega squared L. Is that correct? Seems so. Okay? Now, that's not the hard part of the question. That could have easily be asked in the second midterm. The hard part is now what happens when this first string breaks. So these masses are happily rotating with some angular frequency omega, but suddenly the first rope snaps. It has higher tension, right? So it's more likely to snap. Now, when it snaps, what do I expect these two masses to do? These two masses will do, and they are tied to each other, so they cannot get away from each other. So essentially, they'll do the following motion. Their center of mass will move with a constant velocity. Why am I sure that their center of mass is going to be constant velocity? There are no external forces, which means their total momentum will be conserved. What was total momentum? Total mass times velocity of the center of mass. But that's not it. They'll also keep rotating around the center of mass, right? With a angular frequency omega. So these are the two things we need to calculate. All right? So what are our guiding principles here? What would be, once the rope snaps, what is conserved in the system? Is momentum conserved? Yes, of course it's conserved, right? I mean, what? And these two objects are tied to each other, but they are a closed system. They are in a frictionless table. So momentum will be conserved. So what was momentum exactly didn't I choose a different pen? V1 was omega times L. V2 was 2 omega L. So what's my initial momentum at the exact moment where the first rope snaps? It's going to be, this is m omega L, this is 2m omega L, so it's going to be 3m omega L. Right? How about the momentum anytime after that? How can I write it? Remember, momentum of a system was total mass of the system, right? Total mass of the system is 2m times the center of mass velocity, v center of mass, right? So that's great. P initial is equal to P final. So 3m omega L is 2m times v center of mass, m's cancel. V center of mass is 2/3 omega L. No, 3 halves omega L. Yes.
Would there be angular momentum?
Let's discuss that. Okay, that's exactly what I would like to discuss. Now, how about energy? Do you think energy of the system will be conserved once I cut the rope? This is on a frictionless table, right? These two things are tied to each other, but otherwise not interacting. So I would expect energy of the system to be conserved. Okay, so energy should also be conserved. Now, what's energy in the initial situation? I have 1/2 m omega square L square plus 1/2 m 4 omega square L square. So that gives me 5/2 m omega square L square. How about the energy of this object moving with v center of mass and omega prime? How did we write the kinetic energy of an object that is doing both translational motion and rotational motion? The kinetic energy of this object was 1/2 times full mass, the total mass, times v center of mass square plus 1/2 times I center of mass times omega prime, the rotation squared. Do you remember we discussed that? We said you cannot do it in general, but we can do this separation into translational kinetic energy plus rotational kinetic energy only at the center of mass coordinates. Okay. So that's great. My initial, it's my final, my initial kinetic energy was 5 hells m omega square L square. E initial is equal to E final. 5 hells m omega square L square. That must be equal to 1 half 2m. V center of mass we have found as 3 halves omega L squared plus 1 half. What is the moment of inertia around the center of mass? What was our definition of moment of inertia? R square dm. I have two masses. Both of them are a distance L over 2 from the center of mass. So I should have from the first one m times L square over 4. But I have two of those. So it's small m L square over 2, 1 half. Small m L square over 2 times omega prime squared. Let me quickly do the algebra. I'm running out of time. M omega square L square is m 9/4 omega square L square plus 1/4 m L square omega prime square. L squares cancel, m's cancel. So that's 10/4. So this is 1 over 4 omega square is 1 over 4 sorry? Omega square. So omega prime is omega. Does it make sense? Let me check one more thing. What was my, and let me keep you a few more moments here. Could you close the door? What was the initial angular momentum with respect to the pivot point? M V1 times its length, so it's going to be m times omega L times its length from the pivot point is L, so it's m omega square L for the first thing and 4m omega L square for the second. So it's going to be 5m omega L square. How about L final here? Now we have not discussed what happens to the angular momentum of a rigid body when it actually does both rotation and translation. But here is something I would like to try. First, let me think of the pivot point. These guys started from a distance of 3L over 2, the center of mass. So I'll basically write it in two terms. I'll say there is the angular momentum around the center of mass plus angular momentum of the center of mass. So my idea is that L is made up of two things. It's going to be I center of mass times omega plus R cross P center of mass. Just as I can actually write kinetic energy as kinetic energy of the translation of the center of mass, 1/2 mv square, plus kinetic energy of rotation around the center of mass. I can do the same thing for angular momentum. All right? Let's take a 10-minute break. I'll check that this quantity is actually conserved. Okay?